All right, so this is the second part for the November 8th lecture that I missed. Again, I apologize. So I sent you the notes and just make sure you have the handout and we're going to continue now. We know that 1 to 2 is isentropic compression, so we compress it to increase pressure and temperature. Then with the model at least we have constant volume heat addition, so we know that the temperature and the pressure, both of them will increase. So now we move on to the next process, 3 to 4, and that is isentropic expansion. That means that from that expansion, we're going to get, this is also sent to you, from that expansion, we're going to get work out, because we have, volume that's increasing, so we're going to get boundary work out. And because it's isentropic and every process is reversible, it means that Q is equal to 0 for that one, same as the first one, okay? We have Q minus W delta U, and now I don't have another negative for work because I have an expansion. So then I have that work 3 to 4 is U3 minus U4. So it makes sense. We're going to have high energy minus low energy. It's not the same as the heat exchangers that we saw before, because maybe it was more obvious where we had high minus low energy, but in this case, we have work out, so we expect the energy to decrease. Because we have delta S equal to 0, we can use the isentropic relations, such as what we have there for PR and VR, keeping in mind that V4 over V3 is maximum volume divided by minimum volume, which is also equal to the compression ratio. So as I mentioned before, if you are writing this down, you can include that this is equal to R, all right, the compression ratio, or if you printed out the notes, then you can add that as well. So now if I continue the diagrams, I remember that 1 to 2 was isentropic compression, so there's a curve. We talked about that on the first one. 2 to 3, we have constant volume heat addition, and then 3 to 4, we have expansion, so we're going to get work out. And then 4 to 1, we're going to have constant volume heat rejection. So if we look at that, right, 3 to 4, the volume is increasing. It's isentropic, so that's why we have that curve, which we could, if we wanted to. 3 to 4 on the TS diagram, it's moving down. As we get our expansion, the temperature will decrease. Some people have asked me T2 compared to T4. Well, T4 doesn't have to be higher than T2. It doesn't have to be the same. It doesn't have to be lower. It varies. It could be either one. Okay, not either one. There aren't two options. It could be any of those options. Okay. All right. So then we have 4 to 1, which on the PV diagram is a vertical line down where we have our Q out, and 4 to 1 on a TS diagram, same thing, because it's reversible. Everything is reversible here. Then delta S will depend entirely on Q over T. And because we have Q out, which is negative, then delta S will be negative. And this does not violate the second law, all right? Second law has to do with S-gen, or with a system that has no heat transfer between the system and surroundings, or two systems. So you can look at the PV diagram there. V2 and V3 are the minimum volume. V1 and V4 are the maximum volume, so the compression ratio. We can use that for 1 to 2, and we can also use that from 3 to 4. Now, I just want you guys to remember, right? If we compress it, we heat it up, then it expands. Then at constant volume, when it moves down, let me do it again. We compress it, we heat it up, then it expands, all right? And then here at the maximum volume, we get Q out. So that is what's happening, okay? So then I wrote the equation for 4 to 1, but you can just go straight to using them, especially if you don't understand them. You don't have to redo it, okay? If you understand them, they're here. From 4 to 1 is constant volume, so there's no work, and Q4 to 1 is U4 minus U1. I have a negative there for Q because it's Q out. Now the equation I don't have on my notes, but it's here, all right? It's for constant volume. We know that P over T is constant, which is exactly the same thing we have from 2 to 3, okay? So hopefully you are also looking at the handout, okay? So we have all these equations for each of the processes, okay? And again, we have Q minus W for all of them. We have Q equal to 0 for 2 of them. We have work equal to 0 for 2 of them. And we have P over T constant for the ones where volume is constant. And we have the isentropic relations for 2 of them when they're isentropic. And that's it, right? That's the summary of it. But because it's a power cycle, we have the thermal efficiency is the work of the cycle divided by Qin. So the work of the cycle, because this is a power cycle, the objective is to get work out. We have work out minus work in. We have work out during 3 to 4, work in during 1 to 2, divided by Qin. And that's a function of U. You can see that on your notes, okay? Now, if you look at the handout at the very bottom, before Vmax and Vmin information, we have the mean effective pressure, MEP. And there it says work divided by delta V. We're not going to use that because if you move delta V to the other side, we have that work is pressure times delta V. And that's the equation that we use when we have constant pressure, right, for work. So that would be the pressure of the cycle if everything happened at constant pressure, which is not useful to us at this point, okay? All right, so now before I start the example, we're going to look at the other side of this handout, okay? So this is now in the notes because we already discussed the behavior of each process. So the PV and TS diagrams are still the same. So the other side, cold air standard. Oh no, like we have to do everything again, but then the equations look pretty different. So I just fold it so I don't get confused. You can do whatever you want. So then we have for delta S, actually what is cold air standard, right? Cold air standard. We still use the air standard assumptions for cold air standard. We have ideal gas and just air, and we have a closed system, so we don't have combustion or exhaust, and everything is reversible. But now we're going to assume constant specific heat at 300 Kelvin. That's why it's called cold air. When we see our example, we'll see that the temperature increases sometimes close to 2000 Kelvin. So why 300 Kelvin? I don't know. Yeah, I did not design this. However, why constant specific heat? That one I can answer. With 300 Kelvin, actually it's a good question. I'm going to look it up, okay? Maybe because it's ambient, so it's easy to get the numbers. I'm actually not sure. But constant specific heat. If we use constant specific heat, we don't have to do any interpolation at all. For variable specific heat, a lot of interpolation, okay? Of course, the computer can do that for us. But even if when you go to work, sometimes you have to do it by hand before you move on to the computer, which is it's not bad, right? But then here, no interpolation, which is great. In addition to that, we are making so many assumptions already that it is so far from reality, right? That making an additional assumption doesn't affect it that much, and we can still get a sense of the behavior. So that's the justification. Again, it's not me, all right? Some other people decided that. So what's this? Okay, so a real engine, all right, for a car, the efficiency might be around 30%, maybe lower. If we perform the analysis using air standard, then the efficiency, how long has this been? 8 minutes. The efficiency might be 65% or so. Then if I make this approximation, cold air standard, maybe 68%. So they're both extremely high. So then some people say, or some people have said in the past, well, since they're both pretty bad and this one is less work, we can use this one. I'm not convinced yet. Maybe if I went to work for industry, maybe they would convince me of why they do that. But I am not convinced. I feel like if we have the tools to do this one, we should do this one. When I say this one, I mean the air standard, okay? Because this is the exact way after we made assumptions. This is making the same assumptions, but then also using an approximation for specific heat. Not only that, but we are looking at that value at 300 Kelvin, okay? So your exam has air standard, okay? Actually, I haven't decided. This one's shorter, this one's better. So I haven't decided, but I'm thinking it might be like air standard. Ignore the last 7 seconds or so. All right, so cold air standard, what's happening here? We have the same processes, isentropic compression, constant volume heat addition, isentropic expansion, and constant volume heat rejection. And I might post 3 videos because I want to go over an example. Sorry, I just decided that now. Okay, so for isentropic, for air standard, we have PR and VR, but now we have constant specific heat. So we use the equations for isentropic processes for constant specific heat that we saw in class, okay? You should have that somewhere on your notes, okay? It's also on that handout for ideal gases. So we have that, and we have K minus 1 and K minus 1 and K. And all right, so we have a K there, and that K is specific heat ratio. That's Cp over Cv. And Cp over Cv at 300 Kelvin is 1.4. That's it, all right? You can look that up on table A2B, but it's just 1.4, so I'm telling you now. Now, Q is still equal to 0. You can look at the handout. Work is still delta U, but delta U for constant specific heat is Cv delta T. And if we want actual work and not specific work, we have to multiply by mass, okay? Now the next one, constant volume, heat addition. Constant volume work is still 0. P over T is still constant. So now we have that Q. It was U3 minus U2 before. Now it's mCv delta T, all right? Then from 3 to 4 is isentropic. So we have isentropic relations for constant specific heat. So no PR and no VR, okay? Same thing, Q equal to 0. And work, which was U3 minus U4, is now m. Cv T3 minus T4, or if it's specific work, just Cv T3 minus T4. And 4 to 1, constant volume, so no work. Q, which was U4 minus U1, is now Cv delta T, multiplied by mass for heat transfer, no mass for specific heat transfer, and P over T constant. Now, at the bottom, no mean effective pressure, but the efficiency is still work of the cycle. I'm looking at this. It's still work of the cycle divided by Q in. So now it is still what you see on the other side as a function of U. Because U is Cv delta T. Cv cancels out because it's at 300 Kelvin. And this is one of the reasons why it's used at a constant temperature. Although, you know, it could be used at another one. I don't understand why so low. And that equation can be manipulated to get the very last equation you see on that side, that is a function of R, okay? This equation over here, all right? So we have that the efficiency is 1 minus 1 divided by R to the power of K minus 1. We know that K is 1.4, so what we can see there is that as we increase the compression ratio, which is R, the efficiency will also increase. So that means I could get an R of 100, right? And say, oh, you know, I'm compressing it by a factor of 100. I'm feeling crazy today. And the efficiency will be like 0.84 or something. It's like, wow, 84% efficient in this car. Great. However, you know, if you decrease your volume by a factor of 100, and you start with 300 Kelvin inside of your engine, your temperature is going to increase to a crazy high number, all right? So what's gonna happen is that it probably won't even reach that value before you get combustion, all right? So you might get knocking, for example, which is, maybe you're familiar with that, okay? And it might damage your engine or your system if you're using this for something else, if you increase that compression ratio by too much, right? If you decrease that volume without, what time is it? Well, not what time is it, how long has this been? Yeah, you cannot go crazy increasing that value. There's a limit, okay? One of the practice problems, or one of the recommended exams from the past, they had to plot, so this will be in the study guide, they had to plot the efficiency versus R, and you see that after a while, it doesn't really increase that much, okay? So we don't want to go crazy trying to design it, and then the temperature increases to 20,000 Kelvin. I haven't calculated. All right, so I'm going to stop now, and then the next one will be an example.